Okay, ladies and gentlemen, this video should supplement your notes to go along with the momentum unit. We just finished up looking at Newton's laws of motion and the forces that dictate them. We will be finishing up the semester looking at energy, and momentum sort of bridges the gap in between those two things to a certain extent. Okay, momentum is essentially just mass in motion. The amount of momentum an object has is going to be dependent on its mass and its velocity. And that brings us to our first equation. Our first really important part here is this first equation. Momentum is equal times mass multiplied by velocity. Okay, this right here should technically be a lowercase rho, which is the Greek letter R. But because it shows up inconsistently on different platforms, I leave it as lowercase p equals mv. Okay, the units here, a little wonky. No one came along and renamed this one like Newton did with his, so we are left with just kilogram meters per second. So essentially just the unit for mass multiplied by the unit by velocity. Okay, that being said, we are using velocity in our multiplication there. We know that velocity is a vector, so therefore momentum is a vector, which means it's going to have a direction. A lot of people throughout the last unit were asking me, how do I find the magnitude and the direction? Remember, magnitude is just a number, right? So the magnitude of the acceleration of gravity is 9.8, and the direction is downward, okay? So don't overthink those two items there. Okay, I will be supplying a second video where I will go over a couple different examples within the notes here. Just because I use a different platform to record those, I can't really write on my screen right now. So I'll work through this example here. I'm going to be working on that next actually. Okay, so with momentum, we also have this thing called impulse, right? We would normally be starting to work on our egg drop projects. And the goal with the egg drop project is to, one, control the momentum of our container, and then to also control the impulse on the container when it hits the ground. So to stop any object, I have to put a force in it, onto it, excuse me. We were talking about action and reaction forces. When I push on an object, it's going to push back on me with the exact same amount of force, right? So if I have an egg crashing into the earth, those two items have slightly different masses. So therefore, they're going to have very different momentums as well. So something to think about, starting to get into impulse. It's impulse is the amount of force that's acting on an object over a certain amount of time. And I'm not going to necessarily go through and read through these. I wanted to sort of just come through and highlight these equations. Our second equation here, impulse, which again is ironically notated with the capital letter J. Impulse is going to equal our force multiplied by the time of a collision. So that t is however long the interaction is happening. Okay. Looking at our impulse unit, our impulse unit is going to equal a Newton second. And again, I'll sort of go through the different units and stuff like that in the screencasted examples, just because it's easier for me to write on the screen and show you how things cancel. This is pretty helpful as well. But I want to jump to our third equation just to show you how they sort of tie together. Impulse is also a change in momentum. another way of saying that, and this is sort of how we tie these things together. So through a lot of our problems, we're going to see um, an object is moving and it crashes into something, so it comes to a stop. So that gives us a change in velocity. So we have this change in velocity, which creates a change in momentum, which gives us an impulse, right? That crash or collision happened over a certain course of time, so we could figure out what sort of force was required to to stop that object or to start it as well. So, and again, I'll come through, talk about this example as well. Look through, there's a couple videos and things like that, little extras hidden in here. Again, I don't want to spend too much time reading through the slides here. I'll leave you to do that on your own. Again, just wanted to point out the three main equations we have. Momentum is P equals mv. We have impulse, J equals ft. And then likewise, our impulse momentum theorems tells me that when I have a change in momentum, I can set J equals ft, which also equals m times delta v, which is that change in velocity. So again, keep an eye out for these screencasted examples, which I'll be starting here shortly. And shoot me any questions when you have them. All right, guys, we'll see you.